Today we'll be looking at a class of second-order linear differential equations known as Euler's differential equations. And these equations are of the form a times x squared, d squared y by dx squared. And so we have a constant a plus a variable x plus bx dy by dx plus cy, where c is another constant, is equal to 0. And the reason why we're interested in this class of differential equations is because we have variable coefficients over here given by x. X is a variable, so it is not a constant. And so we will try to find a way of solving this differential equation. And of course, there are other ways we can do this. We can use the power series solution method. But in this video, we'll be presenting a new method that does not use power series. And this method essentially consists of trying to turn this differential equation into another differential equation where we have constants instead of variables. So some way, somehow, we need to get rid of the x squared and the x in this equation. But before we start, we need to emphasize the fact that x needs to be greater than 0 in order to have solutions to this differential equation. One way of getting rid of these variable coefficients is by changing variables. And we change variables in such a way that when we take the derivative of y with respect to our new x, we get a 1 over x factor, which cancels out with this x over here. Let me write it down explicitly. So we need to substitute x for a new variable. So we will call x is equal to f of t. And of course, when we change variables, when taking the derivative, we got to factor in the chain rule. So dy by dx this time is equal to dy by dt, dt by dx. And so when we substitute our variable, we want dt by dx to be equal to, well, 1 over x. And 1 over x times this coefficient over here, x, will cancel out. It will be equal to 1. And therefore, we will get rid of this variable coefficient. And similarly, when we take the derivative again, we need to have something of the form another constant b times 1 over x squared, which cancels out with the x squared over here. And therefore, we turn this differential equation with variable coefficients into a differential equation with constant coefficients. Hence, we said dt by dx is equal to 1 over x. And therefore, we understand that t needs to be equal to ln of x. And there aren't any problems with the logarithm here because x is strictly positive. And therefore, x is equal to e to the t. And therefore, the way we solve Euler's differential equation is by setting x is equal to e to the t. And so this is our variable substitution that we will be using. Hence, dy by dx is equal to dy by dt times dt by dx. Well, that's just 1 over x, because that's what we wanted to get. And so now we need to find d squared y by dx squared. D squared y by dx squared is equal to d by dx of dy by dx. And the reason I'm writing it in this form is because you will see it helps us understand how we can take the second derivative and taking the chain rule once again. And so we have d by dx of 1 over x times dy by dt. Notice here I've just substituted dy by dx by this expression. And so now we need to take the product rule. And therefore, we have, so d by dx of 1 over x, well, that's just minus 1 over x squared, dy by dt, plus 1 over x, d by dx of dy by dt. And so now we need to use the chain rule again. And notice that the operator d by dx, if we use the chain rule, that is just d by dt dt by dx. And dt by dx is just 1 over x. So 1 over x d by dt. And so these are called differential operators. And whenever d by dx operates on a function y, what it does is it multiplies that function by 1 over x and takes its derivative with respect to t. Our expression then becomes minus 1 over x squared dy by dt plus 1 over x times the 1 over x factor from here. So 1 over x squared d squared y by dt squared. Because we have the extra factor d by dt. And d by dt of dy by dt is just the second derivative of y with respect to t. And so this is great because now we have a 1 over x squared factor for the second derivative. And this will cancel out with the x squared over here. So now we will turn this differential equation into a differential equation with constant coefficients. And so now what I've done here is I've replaced the first derivative with respect to x and the second derivative with respect to x with our new derivative form with respect to t. And so what we notice is that the x squared cancels out with the minus 1 over x squared here, as well as the 1 over x squared here. And the x cancels out with the 1 over x, which is exactly what we wanted, because now this differential equation becomes a differential equation with constant coefficients. And therefore we have minus a y prime, where y prime stands for dy by dt, plus a times y double prime, plus b y prime plus cy is equal to 0. And therefore this can be rewritten as a y double prime plus b minus a y prime plus cy is equal to 0. To quickly summarize what we have done is we substituted x with e to the t, and then by expressing dy by dx and d squared y by dx squared in terms of dy by dt using the chain rule, we get a differential equation with constant coefficients. So now what we can do is find a general framework for finding the solutions of any of Euler's differential equations. But this can be quite tedious because here we have coefficients which we do not know. And so finding a general solution can be quite tedious. And so what I'm going to do is solve a specific example of Euler's differential equation, where I set a is equal to 4, b is equal to 4, and c is equal to negative 1. And therefore this differential equation becomes 4 y double prime plus 4 minus 4. Well, that's just 0. So we have minus y is equal to 0. And now we can use the characteristic equation to get 4r squared minus 1 is equal to 0. And therefore, r is equal to plus or minus a half. And so we have two distinct roots, and therefore our solution, y of t, is equal to, let's call the first coefficient c1, in order to not confuse with the coefficient a over here. c1 e to the r1t, so a half t, plus c2 e to the minus half t. But notice, this differential equation is in terms of x, not in terms of t. And so we need to substitute back into the x space. And so the way we do that is by noting that x is e to the t. And we can rewrite this equation as c1 e to the t to the power of a half plus c2 e to the t times the power of minus 1/2, which is just equal to c1 x times to the power of a half plus c2 x to the power of minus 1/2. And therefore, our solution becomes y of x is equal to c1 times the square root of x plus c2 times 1 over the square root of x. And so this is our final solution. Don't forget, once you solve this differential equation, you have to replace t by x in order to get the true solution to our differential equation. And there we have it.